Hello and welcome back to Differential Equations. This is chapter 3 on second order differential equations. So today is the introductory lecture where we introduce what second order differential equations are and take a look at the basic things regarding those equations. So in the first lecture I said that the order of differential equation is the same as the highest order derivative you have in your equation. So in that sense, the second order ODE can be written as a function of independent variable, function, derivative, and the second derivative of that function. So that's everything that you have in here. Now you can also write that if the equation is linear, then it will have the form of some function times the second derivative plus another function times the first derivative plus another function times the function equals some what we will call the driving term, the forcing term, and we'll understand what that means later on when we get there. And then as a special case, which is the equation that we will use most of the time, is the constant coefficient equation. Constant coefficient equation. And that one is just going to be a number in front of y double prime and then a number. Those are constants. So we just have the constants equal, and then you can have, and then you can have your forcing term on the other side. All of these are the ways to denote the differential equation of the second order. Obviously, the first is the most general way, and then you have these special cases, because if you have a nonlinear second order differential equation, it lives in here. All of the linear ones, including constant coefficients, live there. And then obviously the most particular one would be the constant coefficient equation. So the example of something like this would be, let's say, 2y double prime plus 3y prime minus y equal to cosine 4t. So that would be, or actually 4x in this case. Let's do x and y situation. And the example of the one over here, you have any function, so e to the x y double prime plus, let's say, y prime over x minus y equals to whatever, like 2x, doesn't matter, right? So these are linear. Both of these equations that I wrote are linear, right? So all of this is linear. And this one contains linear and nonlinear. Now that's the calculus 3 implicit way to write a differential equation when you just mush everything in. Now this could also be x, right? So it's x or t depending on if you're going to do xy problem, or you're doing the tx problem or ty problem. Can be independent variable, could be whatever you need it to be. It's x if it's problem involving the distance, and it's time if it's in terms of time. So it really depends on what you need in a problem. So the example of a nonlinear equation would be when you multiply y's together, or you have, so maybe something like y double prime plus xy prime equals to, I don't know, e to the x, for instance. So this term killed linearity right there, because you are not allowed to multiply or divide together in any way And also you are not allowed to bury your y's in a function composition, so you should not have y in the exponent of e, or argument of ln, or e to the x, like e to the y, and stuff like that. So there are many ways to break linearity, but since we are dealing with a very narrow set of equations, because this is the entire course is introductory differential equations course, very basic, we are not going to cover more than 0.1% of stuff that is out there, with the entire course, obviously. Um, all of this stuff will be expanded greatly later on in your, not just math courses, but your regular courses. You will find it very you will find very interesting to see that every problem of your thermodynamics is going to be differential equation. Every single one from the day one, and then thermo 1, thermo 2. It just gets more interesting as you go. And obviously most of those problems will have far more advanced stuff than what we are doing here, because again, the entire course we are doing is introductory differential equations course. And yeah. Now let's take a look at equations that we are going to work with. So for instance, thinking about these equations, most of our equations will be of the form, which is exactly what I left on the screen right now. Most of our equations will be constant coefficients. Not all of them, but most will. And these equations have a very interesting way of solving them, which is what we are going to talk about in detail later on in the, I believe, 3.3. We will do the proof of why these equations work this way. But today, with our lecture, we need to understand where these lectures come from. So there are two problems in physics that are perfect to explain this. One would be mechanical systems with a spring, which we call spring mass system, and another one would be the RLC circuit for electrical engineering. Now, being that we can't really see electric and magnetic field, and we can't really see electrical current unless we are measuring with the ammeter, or we are putting up those flakes of metal to align themselves in a magnetic field and so on. We can't see these things, so we always go back to a mechanical system, which is the one that we can see. But as I said, these two systems work exactly the same, and you can draw the same conclusions and draw the same equations from both of those systems. But because we can observe mechanical systems, we usually run there because it's cheaper. It's easier to understand the concept when you can see it than in electrical engineering, where you actually have to measure things and look at the instruments to know which wire has the electrical current flowing through and which one does not. So going through this here, I'm going to use the mechanical system to just derive an equation which we are going to actually use later in mechanical vibrations. We are going to have two sections talk about word problems which will contain mechanical systems in terms of the situations that you can get. And then also electrical problems. I think that's probably the last section of the book that will have a little bit of electrical circuits in it. Now, if this was the regular class, I would be wearing for today's occasion my May the Force Be With You equation t-shirt, where the equation for the force is given as this, and these are the vectors. So you would be able to see this at all times, right, on my shirt. Now, force is mass times acceleration over here. That's acceleration. Change in velocity in time, right? Your gas pedal and the brake pedal, they're both acceleration pedals. One accelerates, other one decelerates. So one is the plus A to your speed, and the other one is minus A to your existing speed. But both of those pedals are acceleration pedals. So now, when you understand that you have the force, right? You see that this m, that's the mass of the object that is attached to a spring. So because we are dealing with a spring mass system. So I'm going to plug in some kind of a mass over here. It's a block of whatever. And then we're going to attach a spring to it. And then we're going to pull this object, let's say, out of the equilibrium, and then the object will just be going back and forth, back and forth, back and forth, back and forth, right, until it eventually stops because there is friction. Now, if I eliminate friction, if I eliminate gravity, right, by moving away sufficiently far from the galaxy, and I have the frictionless surface, so this is the ideal case, right? We're going to have just a couple of forces acting on this object. You are going to have the well, we could add, if you want to add effects of gravity and friction at the same time in this system that you don't want to deal with let's say friction, you can add some kind of a dashpot here which would make the object eventually slow. So it's like a little piston in here, right? And then as this spring goes left and right, left and right, left and right, this one is this system here is effectively slowing down the whole process until eventually it dies out. So when you take a look at the system like this, right, you're going to have the force of the spring. You have the object which has its own mass, right, and then you're going to have the another force over here, which is force of resistance, which is again, could be friction, could be gravity, could be also someone pushing back. It doesn't matter, right? If you want to move the fridge and you push it this way, you have your friend trolling you and pushing the other way. That's Fr, right? F of resistance. Thou shall not pass with the fridge, right, to put it in a location where you want it. So now, if you take a look at the way we solve all physics problems, the way is to draw what we call in physics free body diagram, which is just a mass with these forces acting on that mass. And now students are usually confused, why are these two going in the same way, right, if resistance should be pulling the other way. Well, one thing to know with springs and rubber band is that when the spring is moving one way, the force of the spring is actually pulling the other way, because the spring and the rubber band always want to do the opposite of what they are currently doing, unless they're in equilibrium. So if you stretch the rubber band or a spring, the forces are pulling in. So even though you are stretching the spring out with the vectors going out of the spring to the left and to the right, the forces are pulling in. So these are the things that you need to understand. So the force of the spring is opposite to the way that the spring is actually moving, and the rubber band. Now, obviously, you are members of this planet, so you have seen that, right? The more you stretch the spring, the harder it gets to stretch it, because the spring is pulling the other way as soon as you let go, the spring immediately collapses. The same thing if you compress the spring, right? The spring wants to push out, right? So the force is actually pushing out for the spring. Now the force for the spring is and that negative sign, right, on the spring is called the Hooke's law, and this one over here is the constant, the spring constant, which actually is the only thing that tells you how stiff, how strong the spring is. So if you are thinking about the shock absorber of your observer of your car, and you're thinking about the little spring that you have in your pencil, mechanical pencil, or a mechanical pen, right? That when you click on top, there's a little spring inside. You pull those two springs. Obviously, one is bigger and thicker, but they are actually the same object. They're both springs. They look the same. One is bigger than the other. So the only difference between the two springs is actually that K, because the K measures the stiffness or how hard you have to work, how much force you have to put to compress the spring. Now, obviously, it's much bigger for the car than what you need to, use in a pen, so you can click it with your finger. And now the springs are standard mechanical components that we have in pretty much every mechanical system that exists out there. So understanding the spring is really fundamental for all of the mechanical engineers. So now that K over there is just going to tell us how stiff the spring is, and then you have the X, which is the distance you have to either stretch or compress the spring at this force, and then you will know and understand that spring very well. So that's that part, and then we're also going to have the other part for the dash part, which is, oh, this is Fs. There we go. Hold on. There we go. That's Fs, and we also have Fr, right? And now Fr is negative CV. Now that depends on velocity. Remember that I also had the velocity with the force. So if the object is moving left and right because you set it up into motion, the gravity, air resistance, friction, right, all of those are slowing the object down as the object is moving. So if you have the system that hangs from the ceiling, then the gravity would be the one that slows down the system, and this system would be in a distance dangling like this, and then eventually would stop into the right equilibrium point of the object. See if it's going up and down. So you can model that motion with the cosine nicely, and then have to put some e to the negative x, right, to give it this. Now we'll derive these equations actually, so you'll see physics develop properly from these. The physics is derived from differential equations, so you will see the process of how we get those physics equations from there. So if it's a up and down problem, right, and you can also add air resistance to it as well. So when you mush all of that together, that's all of that is going to go into this C, and then you will have the velocity of the of this object, and then the velocity over here is 0. It stops and then turns out into another velocity going down. And then again, velocity over here equals 0. It stops and goes up and so on. Same thing goes for left and right motion. The mass is going to go to the left, stop, then it's going to go to the right and stop. And the speed at which it goes left and right, which is the velocity, will be impacting the resistance. So more speed, more resistance. Remember how you reach terminal velocity, right? So if you throw an object in the air, the object will eventually reach terminal velocity, and it will not fall any faster. That's why parachutes work, right? With the air resistance and the amount of air the parachute scoops on the way down, the object attached to a parachute, which is usually a person, but it could be, air dropping deliveries. You can calculate, regarding the weight, the size of the parachute, and the terminal velocity, which is desirable to hit the ground with. right? So people don't break bones, or whatever is airdrops, it doesn't break. So all of those concepts, work together, and then we can say, right, that we have our equation for the force, and I'm going to say over here force of that mass, which is the total force, right, is going to be, so the total force of the system is going to be F of the spring, which is force due to spring, plus force due to resistance. And this is the force that is MA, which I also wrote as dV dt, right? That's the force at which the object, right, the total force applied to the mass m. Now I'm going to write this as mass times acceleration, but then I know that acceleration is a second derivative of the position function. Therefore, there we go, mass times dx dt second derivative, sorry, d squared second derivative. There we go. Now on the other side, we have our equation that I said before. We're going to have them as negative kx, and we're also going to have it as a negative cv. Now v, you know what? Let's put this a and then go to the next line and fix all of this. So mass times the second derivative of distance is going to be equal to negative kx minus c, and then I'm going to have dx dt here because this is the velocity, right? Velocity is change in position in time, like miles per hour, right? X is a distance in miles, t is time in hours, so miles per hour. And if I put all of this mess on the same side, we see that we get mx double prime plus cx prime plus kx equal to 0. And since mass is a constant, c is a constant, and k, right, the spring constant is constant, we just derived the second order linear constant coefficient equation. So, and this would be for mechanical systems. So now what I can do here is I can say this is the equation that I am observing a system that doesn't have any outside involvement, right? It's set in motion, and then the system is perfectly described by this equation. So this equation here, which you are going to know, all of you are going to learn this equation, and we'll have one for electrical at the end of the chapter. So this equation is your second order linear constant coefficients ordinary differential equation. There we go. So second order linear constant coefficient ordinary differential equations. This D looks like a P, so I'm going to ODE. There we go. ODE. And we have this piece or equal 0. So I'm just going to pop here it with the orange and say without forcing, meaning that nothing is bothering this system from outside of the system. But if you are going to have something pushing the mass as soon as it gets, so let me give you immediately an example of that so you understand why this other equation mx double prime plus cx prime plus kx equals to f of x, how this gets to play the role. So this is going to be this one, but now I'm going to say with forcing, and now to understand this case, I'm going to make the pendulum like this, on the ceiling, and then I'm going to swing this left and right. Now this is not the spring. Actually, I shouldn't be doing. I'm not going to do that. I'm going to put what is supposed to be, and then I will compare it to the other thing. All right, so here's your mass, right, hanging on the spring. This is where the equilibrium point should be, and then you pull this mass. Let's say you pull it down, pull, and you let go, and it will be going up and down, 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 and eventually it will stop. In 5 minutes or an hour, I don't care. It's going to stop eventually because gravity and air resistance, right? However, if you are doing this, you pull it down and let go, and you never interact with it again, then that's this situation. However, if you give it a tap every time the object is on the, let's say on the bottom here, you give it a tap, then that little tap is you supplying extra energy to the system. You giving it more force, therefore the system will keep going as long as you are, kicking it. And then when you stop doing that, eventually the system will stop, right? Because then your external forcing stops, right? And then it becomes the top equation, which stops due to resistance term. Now, what I wanted to compare this is to the kid on the swing. You have the pendulum, which is the basic pendulum, right? Kid on a swing is nothing but this. That's it, right? And then you push the kid goes this way, then it comes back the other way, and then you are standing here and keep pushing the kid, right? So if you are, both immortal and if you're just both immortal, right, this system would go on forever, right? You pushing and at the same force every time, and there will be no slowing down, right? So that's that f of x or f of t, depending on, again, the problem you're dealing with. So f of x or f of t, and that would be something that pushes. So now a little bit for the actual example. So we're not doing the pendulum here, so we're not doing kid on a swing, but you understand the situation of you supplying the energy to the system constantly, and that's what the difference between the two is, right? If the system is self-propelled without external forces, then that's the top part, and if you do have external forces pop in, then you have this. So technically you pushing the kid at every whatever seconds would be some kind of cosine, I don't know, AT, right? You will be, and then the period of how frequently, right, you push the kid would be given by, right, and you will have some amplitude. This is how hard, right, you push, and then that also plays the role in. But again, the details when we get there. I hope you understand the difference between the two equations, where one is 0 and the other one is f of x or f of t. This actually should be f of t. This should be f of t, because this one is d squared x dt squared. This one is dx dt. This one is just x. And this is a function of time, which is the forcing. This is the forcing term that we use. So this must be t. This must be t. That was my mistake there. So please fix that. Make sure you all have t over here. It's f of t. It's a function of time. How frequently are you pushing the kid on the swing? Again, not the pendulum, but how frequently do you tap this one to go up and down, right? So we have that forcing. Now, in this case, another thing that we are learning is the amount of solutions is going to follow the same rules like when you had equations. Remember that your linear equation had one solution, and a quadratic had two solutions, and a cubic has three solutions, and so on. And then you eventually learn in pre-calculus that the highest exponent, the term with the highest exponent, is the leading term, and the order of that term, the exponent of that term, is equal to the number of solutions. Well, now for differential equation, since we are going one up, right, in terms of concepts, now the order of the differential equations will tell you how many solutions you have. So I have to write this in blood. Second order ODE means two solutions, which immediately means that if you have a seventh order ODE, you have 7 solutions. Now, we have to be more particular about this, and these solutions need to be, when we'll see that, right, these solutions need to be what we say linearly independent. So they are not going to be dependent on each other, and that allows us, now that's not the focus of the story yet, I'm just mentioning that because I'm going to write this as C1y1 plus C2y2, and your two solutions are actually these y1 and y2. So those are the two solutions that you are looking at. The overall solution is linear combination of the two independent solutions. Now, we are learning how to find these as we go through the chapter 3, and then to put the total solution together, which is this y, you can put y of t if you want to, right? That's going to be the overall solution for the differential equation. So it's still going to be one line, but there are two separate solutions inside that line. One is y1 and the other one is y2, and you have two of them because you are solving second order differential equation. Now, these solutions are unique. I mean, they exist and they're unique. So existence and uniqueness equation, existence and uniqueness theorem exists for second order and all other orders as well. And it's the same as the previous one, right? You need the continuity on the open interval, and then, you know, if the stuff is differentiable, you have your differential equation. And there are, and you can have now two initial conditions because you will have two constants. Previously, you only had one constant C, and you needed one initial condition to compute that constant C. Now you have two constants, C1 and C2, so now you need two initial conditions. So in order for us to be able to solve and get those particular solutions, we have to go and use two initial conditions. As usual, if you have any questions throughout this, make sure that you are asking those questions, because, you know, that's the part of you know, having a live class. So if you run into something that you haven't heard before or don't understand, it's time to ask. All right, so let's just do the general equation again. Now, instead of those A, B, C functions, I am dividing everything by that capital A and then renaming them. So that way I am in the mode where this is linear and with the coefficient of 1 in front. Now also note that this is function of x, so this is function of x. So be careful that it's either x's or y's. And for this system, right, we have the initial condition y of a is equal to b0 and y prime at the same point a is equal to b1. Now, what does this mean? It's easiest to understand it if you are talking about kinematics, right, motion. And let's say you fired something up and then it came down, right? So you throw a stone, right, and it drops down. You have to throw that stone with some initial velocity because it went up, right? If you do not put any initial velocity into that stone, then you're just dropping it, right? Then it just falls straight down. Remember, it always has to battle the gravity, and the planet is way bigger than the rock. So if you want to throw the stone or the rock, whatever, you throw it up, and that throw contains initial velocity. Well, didn't we just say that dx dt, which is the first derivative, is a velocity? So the initial velocity would be this b1 in this particular case. And this is the height from which you throw. Because, right, if your feet are on the ground and you call that zero level, you can't swing underneath zero level to start throwing it from the zero level. So if you are throwing the rock up, you are usually releasing that rock when you just pass the height of your head. So for most people, right, that's going to be anywhere from 5 to 6.5 feet, right? Try to toss your pencil above, right? It's your hand will always release when it passes your head, the top of your head. You are not going to throw it from the shoulder level because it's awkward, right? It's just what it is. So this b0 is the height from which you toss, and this is release, right? And then the b1 is the speed at which. So how fast was your arm and your hand that holds the rock, right? How fast they were moving through the air to give the initial, because your initial velocity is the speed at which your arm / hand, right, moves. So now we understand that in order to get the particular solution, we need 2 points rather than 1, because we have to calculate two C's. And we get them by getting one of them to be y and the other one to be y prime. And then, as I said, I used, toss the rock up to understand. So existence and uniqueness theorem is there for us as well for second order. And now we know that the total solution for the differential equation of the second order is going to be that y equals c1y1 plus c2y2, and then y1 and y2 are two solutions that you would get, which are the part of the larger solution. And now we are going to memorize a little bit here because, as I said, we are going to derive this in your, I believe it's 3.3 or 3.4, I can't remember, but it's definitely going to be the part of the first exam, which is the midterm, coming up in a week or two, right? We are talking about the method of solving constant coefficients, and we are going to have a full lecture on it, but now what you need to memorize is the method at which you solve, and then later on I'll tell you why and how that works. So if you have some equation ax double prime plus bx prime plus cx equals to 0. And we are only going to work with the ones equal to 0 for now. You will see what horrors come to the table once you have that as a function. We'll do variational parameters and undetermined coefficients, right? But that is later on. Right now, we are dealing with this. So you will convert this to a basic polynomial by the quadratic equation, which would be AR squared plus BR plus C equals 0. So this is the step you're memorizing. And then you will solve this, and then solution to ODE is y of, let's say, t is going to be equal to, again, you're memorizing this, equal to C1e to the R1t plus C2e to the R2t. And where do you get your R1 and R2? You're solving quadratic equation. It's going to give you two numbers. So let's say that, so I need to box this, and you need to memorize this piece for now. So what is happening here? Let's say you have x double prime plus 5x prime minus 6x equal to 0. So this is your second order linear constant coefficient ordinary differential equation. That's your life. The procedure clearly stated. Convert to r squared plus 5r minus 6 equal to 0, and then solve it. Well, this conveniently factors to r plus 6 r minus 1 equals 0, r equals negative 6, r equals 1. Basic algebra. And all you need to do now is to plug into the solution. So y of t equals C1 e negative 6t plus C2e to the t. Your R1 and R2, well, you can write as R1 and R2. The order doesn't matter. You can write either one first because it's added, right? So who cares? So you have your two solutions now. One solution would be this. The other solution is that. And you have the two constants in front. So this would be known as general solution. And it's general solution because you don't have your C1 and C2. I did not give you initial conditions to compute those, so you don't know what they are. Now, in the second example, I am going to provide those, and I will let you solve it because the solution is a joke. You replace r squared r, and then you solve quadratic. But then I would like to see if you can figure out how to plug in the solutions, sorry, not the solutions, how to plug in the conditions to come up with the C1 and C2. So let's have an equation of literally anything. Looking at the page 3.1 homework, pages 147 in your textbook. And I just want to pick up literally any one of these. But I want to find something that would actually factor so you don't have to. Here, problem number 6. So try this. Y double prime plus y prime minus 6y equal to 0. And initial condition is y of 0 equals 7. And y prime of 0 equal to -1. So I'm going to mute myself and go check on the homeschooling upstairs. I told you this is ridiculous. Our idiotic government is way out of control with the closures and things anymore. So I have to go and check, see if they're still alive. And then I'll be back. So try this problem. I'll be back in a second. Well, actually, this doesn't mute the YouTube stream, so whatever. I'll be right back. All right, if you wondered, they are alive, and whether they're learning anything, that's obviously. All right, let's take a look at the solution here. I hope you had the chance to figure it out for yourself. We start by converting it into r squared plus r minus 6 equals 0. So that's always the first step. And even later, 3.4, 3.5, 3.3, 3.4, 3.5, when I solve this problem and show you the proof of why this conversion is possible, you will still be doing it the same way. We're not going to learn a new way. I'm just going to prove and show why this method works. So you convert everything to R's, then you do your factoring. If you can't factor, you are going to use quadratic formula and come up with fractions, decimals, square roots, complex numbers, not a part of this one, right? So you can come up with any one of those, and you have your R is -3 and R is +2. Now, if you have them as 2 and then -3, I told you it's the same thing. Doesn't really matter which one is first, which one is second. Now you will write your solution with the equation C1e to the -3t plus C2e to the 2t. I hope you all have at least this much, because this is considered a joke up to this point. And now we are supposed to use this to calculate C1 and C2. Now, clearly, you can plug this one directly into this equation, right? This is t is equal to 0 and y is equal to 7, and that's simple. Now, this one over here plugs into the derivative. So you can't plug the second one until you find the derivative of this solution. So that's -3c1 e to the -3t plus 2c2 e to the 2t. So this equation is getting t is 0, y is 7, and this equation is getting t is 0, y prime is equal to -1. So I'm just gonna leave that there for you to stare at it for a few seconds. I'm also going to say this is your general solution. There you go. Any questions, concerns?
This was easy.
Yeah, I'm sorry. That's the best answer I can give you. So don't worry, it will make up once you hit those variation of parameters and undetermined coefficients. Trust me, it will make it up. So 7 is equal to C1. Now, guys, e to the 0 is 1, right? So C1 plus C2. And -1 is equal to -3c1 plus 2c2. That's your life right now. So you will plug your one equation, right, one point into appropriate equation, the other one goes into the derivative, and you come up with a system, 2 equations, 2 unknowns, and you just solve it. Whatever witchcraft you can pull off, no one cares what you're going to use. Elimination, substitution, guess and check method, matrix, literally anything, because this is your pre-calculus and algebra, elementary algebra, right? So you have your C1 plus C2 equals 7, and -3c1 plus 2c2 equals -1. Solve it any way you know. Probably most of you multiplied the top equation by 3, right? To kill C1. That made this 7 into 21. That's okay. I mean, you can deal with it. So you have your 3c1 plus 3c2 equals 21. And then copy the second equation as is. When you add them, the first term drops. This becomes 5c2 equals 20. And there's your c2 is 4. If c2 is 4, then c1 better be 3, because they have to add to 7. You have your equation. Now you have your c1 and c2. So y of t is equal to c1 is 3, so 3e to the negative 3t, and then plus 4e to the 2t. And this would be known as a particular solution because you calculated your C1 and C2. And that's that. Now, I hope that some of you had e to the 2t first. You still got 4, right? Even the term was here. You still got 4 to be its coefficient. So it doesn't matter where you put 2 or where you put negative 3. The 4 will always go, for this problem, 4 will always go with 2 and 3 will always go with negative 3, no matter which way you put these together. Now, do we have any skeptics that go, is that really a solution? No? No one cares that this might be wrong? You can check, right? And the check is you take derivatives and you plug them in the original differential equation, work some algebra out and make sure that it works. So you will find y prime, that is negative 9e to the negative 3t plus 8e to the 2t. And you also need y double prime, because you need to plug that in as well, which would be 27e to the negative 3t plus 16e to the 2t. Your differential equation was y double prime plus y prime minus 6y equals 0. And this goes there, this goes there, and your solution goes there. So it's going to be, right, 6 terms plus multiplied by negative 6. So we have 27e to the negative 3t. Looks like a 7, it should be t. Plus 16e to the 2t. That's me plugging in y double prime. Then I have a big fat plus from the differential equation. Then I have my y prime, which is negative 9e to the negative 3t plus 8e to the 2t. And then I have minus 6 times, and then this is 3e to the negative 3t plus 4e to the 2t. And now what do I have? I have like terms here, here, and here. So this is negative 9, and this is negative 18, together negative 27. So they all cancel. And what else do I have? Let's go rainbow. I have 16 plus 8 and then minus 24. Well, 16 plus 8 is 24, 24 minus 24, so they cancel. And you get big fat 0 equals 0. You did have 0 on the right-hand side of the equation. When you added all of these terms on the left, they added to 0. So 0 equals 0 means that the solution we have is correct. And again, I will say, I know I said this before, I'll say it again. The reason why I absolutely loved differential equations as a course, as a student, by far was my favorite course of all math courses I took, was differential equations. I actually took it at RVCC as a student. I took a lot of math courses over, 11 years plus graduate school and all of that stuff. The reason why I love differential equations so much was this, the blue stuff. I had never had to walk away from homework, exam, any problem, and hope I did well. I just knew I had 100 like that, right? Because you can check every problem. These are equations, which means that provided that you are not lazy and you care, you can always check this and have the result that you desire. It's just that, laziness part that gets in the way for most of the students. They say, yeah, it looks good, right? And then you made a 1 minus sign oversight, let's say here, which is even the algebra part, and then it all goes to hell because of that 1 minus sign. Usually where students mess up is they forget to multiply. 7 times 3 is 21. So they copy 7 here. And that just takes everything, out of. So I hope that, you would check, because as you see, it's a joke. It takes a minute or two to check. And I know this problem is good. And I walk away at that point. So we have seen 2 problems. You already mentioned that, yeah, this is way too easy. Okay, fine, all good. We're not learning anything, way more complicated today, but we do have to take a look at 2 more things. The concept of independence, which I mentioned earlier, where the 2 solutions need to be linearly independent. Now, something like that should be, dare I say, common sense within an equation like this, because if the y1 and y2, if those were not linearly independent, then you would be able to factor them, right, and put them into the same y. So if one of my solutions was 3e to the 4t, and another solution was 7e to the 4t, well, then you just mush them together into 10e to the 4t, right? So we have to be careful, right, that we are actually getting what we call linearly independent solutions, meaning that we cannot add them together into a total one term. We have to have 2 separate solutions because you started your journey of the second order differential equation with this knowledge that second order 2 solutions, third order 3 solutions, right? That was one of the first things I said, right? So the amount, the height of the order is going to be the amount of solutions you have, and they're always the same. So in that respect, it's like taking square roots. I'm sorry, it's like taking square roots, right? And you know that if you square root both sides, you're supposed to put plus and minus. So if you have x squared equals to 4, and you square root both sides, you better put plus minus here, because that works out to be x equals plus minus 2. Because both negative 2 and positive 2 are solutions of x squared equals 4. No matter which one of these you square, you will get positive 4 on the other side. If you do not put plus minus, then you are losing one solution. You are only 50% correct. And that's for the square. X cubed equals 1. 99.9999% of people will just say, oh yeah, x equals 1 and move on. How about the other 2 solutions? Yeah, I know they're complex, but they exist. It's just that you are a terrible discriminating person, right, that doesn't accept complex values in our society. And then you discriminate against the complex solutions, and then you just say, okay, one of them. But there is also negative half plus root 2 over 3 I, right? And then the other one with the minus in between. Complex conjugate pair. You have three solutions to the equation x cubed equals to 1. 1 is real, 2 are complex, but 2 plus 1 is 3. 3 solutions for the cubic equation, right? So now, going back to our differential equation, second order 2 solutions. Second order 2 solutions, and those solutions must be linearly independent in order for us to always be able to write them separately, right, and have them as the 2 solutions. Now, the to check for linear independency, right? To check, this needs to be written in blood. Hold on. To check if y1 and y2 are linearly dependent, we use something that is called Wronskian, and we have to learn what that is and how to compute it. So we use Wronskian. Now this is actually the last name, so you made it in life where your name becomes the name for something, right? Even better if it becomes a verb, like we're going to say later. So you'll just Laplace both sides. Laplace is the last name of the mathematician who came up with Laplace transforms. That's going to be our chapter 7. Anyway, so what's about this dude Wronskian, right? So this mathematician figured out the way to use the determinant of the 2x2 matrix to check for independence of the solutions. So the Wronskian is defined as y1, y2, y1 prime, y2 prime here, and that is equal to, when you solve the determinant, I will explain all of this stuff, especially for you who never had matrices before. And then we have y1 prime, y2. And we need this, right? We need this to be different than 0. Okay, so this is what you are remembering, right? So that's your theorem. To check if y2 and y are linearly independent, we use the Wronskian. Wronskian is actually this particular matrix, that it's a 2x2 square matrix, right? And then we use what we call the determinant, which is why these look like absolute value. Otherwise, matrix should have brackets for entries. But when they have these straight lines like absolute value, that means the determinant. Now, to learn the ins and outs of this, we have a whole course called linear algebra. So I'm not going to get into those details. I'm going into the details of how this whole thing works. So what we had in our previous example are two solutions. You can drop the constants, or you can bring them with you. I don't care. I'm going to drop the constants so I don't have to go into high numbers. E to the negative 3t and e to the 2t. So we have e to the negative 3t and e to the 2t, and then its derivatives on the second row. Now, for those of you visual learners, the way to solve the determinant is to go like this. So you multiply a diagonal moving in from the left, and then you subtract the multiplication of the diagonal as you're exiting to the right. Now, many years ago, students said, oh, that thing in the middle looks like a times. You know, when you say 3 times 4 equals 12, right? This symbol. So there's your times there. And then this flat piece over here looks like a minus. So the formula is kind of coded in if you draw this line. So multiply these two, and then subtract multiplication of the other two. So literally, you can just whee, and you're out. So multiply the diagonal, I get 2e to the negative t minus, and over here I get negative 3 e to the negative t And when you put all of these together, you get 5e to the negative t, which is not a 0, and we're good to go. So not zero means solutions are linearly independent, and you do have two linearly independent solutions. You're okay to go with your y1, c1, blah, blah, blah. So, but if you get 0, then solutions are dependent, and then you're doomed. Okay? So let's create that situation, right? Where the Wronskian is going to go, whoa, right? Hold on, Skippy, right? So y double prime, let's say, plus 10y prime plus 25y equal to 0. So here is the solution that is going to have two solutions that are dependent, and then we have to perform some witchcraft to actually get the solution. So in this particular situation, when you do your r squared, well, actually, you know what? I'm going to go grab a bottle of water and check the stuff. I'm going to ask you to do the factoring and all of that stuff. I'm just going to grab a bottle. I'll be back in 19 seconds. Okay, so let's take a look. Did I mute this or no? No, good. So, I hope you discovered that this is the perfect square, like the square of binomial. It factors into r plus 5, r plus 5. So r plus 5 squared equals 0. And that gives you that r1 is equal to r2, equal to 5. And if you try to write the solution, you are getting exactly the situation that I told you you're not allowed to have, where you get c1 e to the 5t plus c2 e to the 5t, and then you can just put them together, right? So if you check the Wronskian, right, if you want to come right from here and write e to the 5t and e to the 5t.
Professor?
Yes.
It should be minus 5, right?
Oh, yes, thank you. Minus 5. Yeah. Perfect. Thank you. So if you use these two, you will see that the Wronskian is going to come out to be 0. And we know that's a bad situation, right? So multiply this way, you get -5. When you multiply this way, e to the -10t, and then minus another -5 e to the -10t. Minus and minus make a plus, and it's a 0. So we cannot have these two to be the solution. However, remember how I said that there is a witchcraft that fixes this? So what's a witchcraft that fixes it? When you have repeated solutions, you multiply one of these with the independent variable as well. So your solution now should be C1e to the RT plus C2te to the RT. That's the witchcraft that fixes the problem. Now, there is a mathematical theory, obviously, behind that. It's not arbitrary. No one dreamed of it and just, put it down and said, oh, look, right? There is a whole proof and derivation for something like that. Most of this stuff is, in the honors course anyway. But given the fact that you don't have your R1 and R2 anymore, they're now the same -5 in this particular problem. Given that you have that, you now are coming up with this, which is the solution for what we call repeated roots, right? So that's the solution that we have. So repeated roots, and it looks like this. So so let me now give you a problem that you will solve from scratch, right? And then also figure out C1 and C2. I guess Zoom crashed or something for my kids. I'm just gonna go check that. And this is it for the lecture, right? So this will be our last example. So you work this out, and I'll be back to check and work out the problem in like 2 minutes. So let's go with y double prime minus 12y prime plus 36y equals 0. Y of 0 is 9, and y prime of 0 is literally whatever, doesn't matter, 6, whatever. All right. Make sure, right, that you have that in the solution, and I'll be back in a second. Zoom updates and crashes. All right, let's go. We replace the r squared minus 12r plus 36 equals 0. And this will put it into r minus 6 squared equals 0, where r is 6. Since the roots are repeated, we write y of t is equal to c1 e to the 6t plus c2t e to the 6t. Now we need to, so that's a general solution. We need to differentiate, so we have an equation to plug the other point in. So we need a y prime. Now, easy for the first one, c1 6c1 e to the c2. The second one is what?
A product.
Product rule. Hello, Calc 1, huh? So we're going to have copy the first, derivative of the second, plus copy the second times derivative of the first. And that simplifies into 6c1e 6t plus 6c2t e to the 6t plus c2e to the 6t. So for the first one, we have t equals 0 and y equal to 9. And the second one has t equals 0 and y prime equals to 6. All right, so when we have zeros, all of these e's go to 1. But look at this, guys. When t is equal to 0, this term dies. So the first equation gets you your c1 immediately. So we have 9 is equal to c1 times e to the 0 plus c2 0 times e to the 0. This term is 0. This thingy is 1. So you're getting c1 equals 9. And you don't have to solve the system of equations, because now you can feed all of this into your second equation. Your y prime is 6. Your 6 times c1 is 9 e to the 0, plus this term is a big fat 0 because of the t right there. And now you have your c2 e to the 0. So this is going to be 6 equals to 54 plus c2. c2 is negative 48. So now our solution, y of t, is 9e to the 6t minus 48t e to the 6t. And this is going to be your particular solution because we calculated c1 and c2. Now, instead of spending time on checking this, right, we're going to do Wronskian to make sure that our solutions are independent, right? So just want to check the independence, even though I told you they are independent. But then why would you trust me? So we plug the two solutions in the top row of the matrix, and then we put derivatives in the bottom row. So the bottom row, here we have 6e to the 6t. This one is still a product rule, so yeah. Copy the first derivative of the second. So that's going to give us another 6 out there. And then copy the second derivative of the first. So it's just this. And we know that we are supposed to go wee, right? So you multiply through, we get 6t e to the 12t plus e to the 12t. That's when you multiply this into both of these guys here. You get two terms. And then we have minus multiplication of this diagonal, which is t e to the 12t. And you see that the total of this is 5t e to the 12t plus e to the 12t. And that's different than 0. Therefore, the solutions are linearly independent, and we keep both of these solutions.
Didn't you drop your 6 on the BC part?
BC part. What is the BC part?
Like for the determinant?
Oh, this way?
Yes.
Yeah, I did. Yeah, I did. Okay. So that's just going to cancel those two terms. Okay. Okay, so the solution is this, which is different than 0. Okay.
Sorry, it's just pretty.
Thank you. No, that's good. I mean, I was just testing everyone, and only you passed the test. You know, just want to see who's paying attention. Too bad you can't see my face now, but good. Okay, yes, you're right. I did drop that 6 there. So that's it. This proves that solutions are linearly independent. So this is good. I did not do the check to plug it into the original differential equation and make sure everything works well. And that concludes. Now, that concludes 3.1, Introduction, where you learn that there are linear and nonlinear second order. You learn that they should have two solutions, which we can put into one line by putting in that C1 and C2 and adding them, which is called superposition. We learn existence and uniqueness, and we need those initial conditions. One initial condition is a point, the other one is the derivative, right? And then the way to go from general to particular solution to compute those C's. And then we looked at the constant coefficients. We looked at distinct real roots and repeated real roots. We did not do complex yet, but that's coming up, either 3.3 or 3.4. We'll do the complex ones as well, and we'll add them to this mix to complete the set. So you can have real roots distinct, which is when you can just list one term with R1 and the other one in R2. Repeated roots, where you do the T witchcraft, right, to make them linearly independent. And then we'll see for complex later on, it's going to be trigonometry involved, sine and cosine. But that's when we get there. And you use Wronskian. Now, Wronskian is generally a question, right, on your exam and the final and so on. So ability to do Wronskian is important. You need that, especially later with the more complicated, equations and so on. You want to make sure that your solutions are linearly independent. Next class, which is Wednesday, we are going to go into 3.2 and talk about the higher order for some time. General solutions of any linear equation. That means, 7th order differential, 37th order differential equation, which we generally never use, but hey, it's one of those sections. Look, Ma, what I can do, right? And finally, next class as well, we move into 3.3 to talk about the constant coefficients. So this story from scratch, and we will add complex roots into the mix. So we are going to learn new stuff. So, questions, concerns? Just the crickets on the other side, I see. Okay. Well, I'm always proud of myself for being this perfectly clear. there are no questions in differential equations. Right? How amazing am I? So I will see you all on Wednesday or during the office hours, and exam in about a week or two. So keep working this. I'll open the homework now. Bye.